Good morning, everyone. I'm Abuzar Fredi, and I'm a recent graduate from UMBC, now working at Amazon. I'm going to present our paper titled Predicting Score Distribution to Improve Non-intrusive Speech Quality Estimation. This work was conducted during an internship in the Audio and Acoustic Research Group at Microsoft Research. Deep noise suppression models are increasingly being used to remove background noise, reverberation, and distortions from speech and are widely used in telephony and voice applications today. These models are occasionally prone to introducing artifacts and lowering the perceptual quality of speech. To understand this, let's take a look at the performance of two DNS models that tries to remove AC background noise while a person is talking. So here's the original sample.
What I'm saying, but those techniques have to be guided by some sense of like
Here's model 1
what I'm
output.
saying, but techniques be guided by some sense of like
And here's model 2 output.
what I'm saying, but those techniques have to be guided by some sense of like
We can already sense that model 2 output sounds a little bit better than model 1. But how do we actually quantify the differences between the two models? One way of quantifying the performance of these DNS models is to employ highly controlled subjective listening tests. So ITUT P808 is one such online crowdsourcing based, highly reproducible subjective testing framework. And it has been shown to stack rank noise suppression models with high accuracy when each model is tested as an average over a statistically significant number of clips. During these tests, several subjects from 5 to 30, for example, are given audio samples and asked to rate the perceptual quality. There are 5 ratings ranging from excellent to bad, the excellent being the highest 5 and the bad being the lowest one. MOS is the arithmetic mean of the scores from the subjects. So, what happens when we give our test sample from the previous slide to the judges? Once they hear the sound clip from the two models, we take the mean of their ratings, and our human listener judges rate model 1 output as 1.3 on average, and the model 2 output was 3.22. So we know model 2 is superior. But in reality, there might be hundreds of models and thousands of audio clips to evaluate. So employing these subjective listening tests can quickly become tedious, expensive, and time consuming. Deep neural network based MOS estimation models have recently emerged as a popular and cost efficient alternative to these tests. The non intrusive nature means you don't always need to have access to the clean speech signals to train them. However, these end to end models require a lot of supervision. These models are trained with only the MOS labels, and the secondary statistics of the opinion scores are generally discarded. So, one school of thought explores whether providing auxiliary supervision would improve the MOS estimation. For example, MBNet jointly predicts MOS and a bias term to account for the difference between the MOS and individual judges' scores. But it might not be compatible with the common crowdsourcing based annotation workflow. On the other hand, MetricNet jointly models PESH estimation with clean speech reconstruction, but it is intrusive by design, and PESC correlates poorly with human ratings when evaluating speech enhancement models. So, in this work, we hypothesized that learning to predict the higher order moments, for example, variance or histogram information, jointly with the first moment, that is the MOS, should lead to a better prediction than just learning to predict the MOS. So we developed models that incorporate variance or the standard deviation, median, and histogram brings of the opinion scores as the secondary statistics. And we explored multiple ways to incorporate the auxiliary supervision. For example, we can directly learn to predict the secondary statistics jointly with Moss prediction, or we weigh each of the samples with their respective variance as a means to incorporate the uncertainty in the loss calculation logic, or directly predict the opinion scores themselves. So let's take a look at the dataset used in our experiment. The dataset is derived from the InterSpeech 2020 Deep Noise Suppression Challenge, and it was obtained using P808. Almost 122,000 unique files comprising both noisy and clean speech are first processed through 320 unique noise suppression models and model variations. We only take the files that are between 4 and 20 seconds in length and consists of only single channel 16 kHz samples. The process generates a total of 420,000 files in the training set. As we can see in the chart on the right, the majority of the MOS ratings are between 2.5 and 4. A sizable number of the samples have opinion scores with a standard deviation greater than 1, indicating a high amount of subjectivity in the opinion scores. The skewness of the opinion scores distribution ranges between minus 1.75 and 1.75, indicating that the median of the opinion scores is often different from the MOS scores. The majority of the samples are platycratic. That means most of the samples are free from extreme outlier opinion scores. And the majority of the samples have 5 opinion scores. That's like 75% of them. Here's a brief overview of our model architecture backbone. The 16 kHz monaural samples are first pre-processed by STFT transform with 512 samples per frame, that is 32 millisecond, and 150 samples overlap. And thereafter, 26 mil frequency bins per frame are extracted. We perform power to decibel conversion on the resulting male frequency bins to better align the features with the human perception of sound levels. This results in a 26 by n shaped feature matrix per file where n can be of varying length due to the input audio samples being between 4 to 20 seconds long. So we utilized a convolutional LSTM based architecture throughout all of our experiments. We employ 5 convolutional layers to gradually decrease the feature space size before feeding the resultant features to an LSTM layers. The LSTM layer helps to build a fixed length representation from variable length convolutional feature sets. And we employ Adam optimizer with a batch size of 256, and the 51,000 parameters of the model are trained up to 100 epochs. The backbone that we introduced in the previous slide constitutes our first baseline, where we only use the MOS labels for the predictions. We also have a second baseline, DNS-MOS, which employs a convolutional multi-stage self-teaching framework. But this baseline is mainly used for sanity checks rather than pure performance comparison, as DNS-MOS employs a more sophisticated multi-stage self-teaching architecture compared to our backbone model. And we also employ 3.5 times more audio samples in our training regimen. However, we do use the same test set from the DNS-MOS paper to evaluate all proposed models. Here is a list of models that we actually developed. In a single task MOS estimation setup, we integrate the variance information during the weighted mean calculation of the loss per batch, which can follow either inverse variance weighting or linear variance weighting strategy. We also propose several multitask models which can be categorized into 3 groups: MOS plus secondary statistics prediction, or histogram prediction, and then the direct opinion score prediction. So let's take a deeper look into each of the proposed models. We first take a look into single task MOS estimation with variance weighted loss. In the inverse variance weighting strategy, weight of each sample is calculated as 1 over sigma I plus delta, where sigma I is the standard deviation of the scores for the ith sample and delta is a small constant. This strategy has a tendency to assign very high values to sample with low variance. To mitigate that, we also investigated linear variance weighting. Samples with the highest variance are assigned a weight of 0.1, and sample with the lowest variance are assigned a weight of 1. And then the weight of the remaining samples are linearly interpolated between 0.1 and 1. The first multitask model is where we predict MOS with the secondary statistics jointly. We just add an extra regression head to our backbone model to predict the standard deviation or the median. The next multitask model is histogram prediction. In this case, the final layer of the backbone predicts a 5-min histogram of the opinion scores. Since the number of opinion scores in the ground truth ranges from 2 to 30, the 5-min histogram creation provides a consistent way to represent opinion distribution. We experimented with 3 different loss functions: cross entropy loss, Wasserstein loss, and chi-square loss. The final MOS prediction can be derived by taking the weighted average of the mean values. The final multitask model predicts the opinion scores directly, and we designate 5 neurons in the final layer of the backbone model as a representation of 5 judges, since 75 of the samples actually have 5 judges. Now, it is not possible to directly compare the predicted opinion scores with ground truth, since judge ID and orders are not consistent across samples due to the crowdsourcing employed to annotate the samples. So we instead calculate the MOS, standard deviation, and median of the scores from the 5 neurons and compare them against the ground truth. We experimented with 2 activation functions in the 5 neurons. The first one is ReLU, and then we also investigated modified sigmoid, which is actually 1 plus 4 times sigmoid x. So the output is hard bound between 1 and 5. To evaluate the models, we use correlation measures such as Pearson's correlation coefficient, Spearman's rank correlation coefficient, as well as error measures such as mean absolute error and root mean square error. Now, there are actually 2 ways to generate these 4 metrics. First is the more common way of per file basis, but we are also interested in evaluating the relative performance of the DNS models. So we group the evaluation samples by the DNS models being used to generate them, and then we calculate the evaluation matrix on those groups, which is called stack ranked evaluation. So here's the sanity check between our baseline and DNS MOS. Our baseline model 2 achieves similar stack ranked SRCC to DNS MOS model 1, and we take a deeper look into the distribution of the predictions, and we can see that the predictions of DNS MOS are heavily compressed between 2 and 4.25 range, while our convolutional LSTM baseline predicts a broader range between 1 and 4.7. The difference in the model architecture and the training set size is the likely cause of this discrepancy, but it needs further investigation. But we can conclude that our model is performing adequately. This was the reason for the sanity check. So now now that we have performed our sanity check, let's take a look at the rest of the model's performance. As we can see, in almost in every case, additional supervision leads to a better performance over baseline model 2. So we will take a deeper look into these results in the next few slides. Among our single task experiments, inverse variance weighting model 3 drops SRCC by almost 4%, while linear variance weighting model 4 improves SRCC by 0.5%. Among the histogram prediction models, cross entropy and chi-square loss provides almost 0.28 stack ranked SRCC improvement over model 2 baseline. We take a deeper look into this at the upper right table, where we lay out the SRCC for each bin, and we can see that all 3 histogram prediction models struggle to predict the accurate probability of score 3 bin. We compare the ground truth and the prediction from model 7, that is the cross entropy loss, in the figure, and we can see that it tends to predict a higher value for score 3 bin, which explains the lower SSCC in that particular bin. According to the stack ranked PCC and SSCC metric, predicting MOS and variance scored together, that is model 5, results in the top performance improvement compared to model 2 baseline. In the rest of the 6 metrics, however, opinion score prediction with ReLU activation, that is model 10, and MOS with median and median score prediction, that is model 6, are top 2 performing models. Opinion score prediction with ReLU activation achieved the highest improvement in RMSC and SRCC. To further investigate how Model 10 generates the top result, we plot the distribution of the activations from the final 5 neurons of Model 10, and we can notice that the first 3 neurons tend to produce higher scores than the last two, and the last two neurons also produce scores with relatively high variance. So in summary, we found that DNN-based MOS estimation of speech signals produced by DNS models can be improved by adding auxiliary supervision on the original distribution of the scores. We demonstrated several ways this extra supervision can be incorporated. Direct opinion score prediction seems to consistently generate the best results among all the proposed models. And this benefit is practically free since during the data curation process, such as in P808, these statistics are typically available but discarded during the model training. We would like to note that the results were obtained with limited hyperparameter search, and our multitask learning setup do not employ any loss balancing technique. For simplicity of exposition, the backbone consisted of a simple convolutional LSTM model, and combining auxiliary supervision with more sophisticated architectures such as a teacher-student model from DNS-MOS has the potential to bring substantial performance improvement. We'd also like to explore other options to include different types of auxiliary labels. For example, we can try to incorporating higher moments such as skewness or kurtosis, or background noise quality labels from recent speech quality assessment challenges and dataset, and soft labels regarding the reverberation of the speech signals, for example, energy ratio C50 or reverberation type T60. A combination of these presented approaches might also be a possible direction for investigation. We'd like to thank Sebastian Braun and the rest of the members of the audio and acoustic research group at Microsoft Research for their valuable feedback, and also Hari Dubey and Ross Cutler from the IC3 AI team for providing the dataset for the experiments. Thank you all for listening to my presentation. I would love to hear from you during the Q&A session. Feel free to reach me or my co-author regarding any query or feedback.